And that's really an IT thing.
I do appreciate your help.
Oh, no, I like hardwire connect. And I tell IT guys that they say, well, hardwire connects secure. I'm like,
yeah,
it's the same thing.
Right.
It's the same thing. This is
You
a hardwire connected.
As you can see, very, very careful. I have everything, right? Two types of things.
Yeah.
My own style, I just try to,
I give you a paper preparation. I give IT an F for not giving us a hardware because they need to do hardware. But everywhere I go, the universities are vectors for lots of students do stuff.
Right.
And so they're cracking down. All universities are. And it's causing a problem for us. We need 100 up.
What's the name?
I'm Joseph.
Joseph.
I'm a contractor. But they changed starting about 2 months ago, they changed the IT protocol. So this used to be an open computer. Didn't even require a lock. And then they locked it down.
I think the easiest way is, you have some HDMI or this kind of thing, just allow every computer to be logged in.
Well, that's what I told them. I said, I need a switch to where they can just push a button to connect ahead of time and push number 1, number 2, number 3, their computer comes up. The problem is that because that's the Zoom computer, we pull the HDMI out of there, it's going to lose the sound because the sound carries over HDMI. So that's what the integrators don't think about. They think how it looks on paper, and I have to make it work in the real world. So fortunately, guys like me are talking to the integrators now, and we're going, no, you can't do this. You can't make challenges. It's got to be very good. And this is a problem we're having all over town, everywhere we work.
Okay.
IT is like ruining our world. And I don't blame them. We have a lot of issues on IT because the hacks that we have.
Yeah.
So they're cracking down, but I said, it's not your presenters hacking.
Right. But hopefully the internet will be stable.
Yeah. Well, I told them turn off the devices. What happens is everybody logged on and clogged the pipe. So it's just like trying to shove a bowling ball in a water hose.
Right. Yeah, we need an amplifier.
Yeah.
Amplifier for the internet.
Yeah. Well, they just need. My recommendation is going to be to give us a hardwire asset here.
Exactly.
And then however that looks, they're going to do it because we can't. I guarantee you, if this happens.
You think this has to be upgraded?
Yes. I mean, if this happens to the dean, if this happens to the dean, IT will fix it.
The camera is not my fault.
No, I'm going to tell everybody at the end of the day, thank you for your patience.
CR. Yeah. Give this to the audience who ask the questions.
It's usually better
small
one person holds. So if you want to be the runner, then say I pulled it, speak into it, safety purpose. I'm not that I'm a COVID expert, but we had to do all year. That was better place.
Thanks. All right, okay. So welcome back. I'll just take over 15 seconds to let you know what's happening. The university, Rice University network system chose today to have some issues. And it's not in this, this building, this auditorium, it's the university-wide issue. And the IT department of Rice University is working on it. So we'll try our best to get the webinar part of this workshop to be connected and hopefully it will be okay. But if there are issues, we'll have to make a decision when the issues arise. So just give you a sense of what's happening.
Okay, thank you. I'm David Abigail. I have the pleasure to chair this next session, which I guess is going to be a bit long because we have an extra talk and then there are the poster presentations at the end as well. So let's just get straight on with it. Fan Zhang from University of Texas in Dallas.
Okay, so first of all, thank the organizers for putting together this wonderful symposium. And also, thank, our Joseph, who, helped us, make everything come back to normal. So my talk is about high-order topological materials. So the previous two speakers already gave wonderful talks, and that makes my job very easy. So first of all, I would like to show you one picture. Okay, so on the bottom of this picture, probably you can see there is one-dimensional edge as a boundary between the sand and the ocean, right? That's kind of a one-dimensional edge. And in the center of this figure, there is also a one-dimensional edge. We call this as hinge, which is a boundary between the two different surfaces, the top surface and the side surface. That's kind of the definition for hinge. And as you can imagine, you can also figure out the contrast between zero-dimensional end state and zero-dimensional color modes. So here comes our definition for high-order topological matter. So we really want a system which is fully gapped, but there are protected gappy states only on boundary of more than one dimension lower. So here are some examples. So this one is the ordinary topological insulator, a three-dimensional one. The bulk is insulating, there are surface states. And this one is a representative second order topological insulator, the bulk and surface, so both are insulating, but there are hinge modes. So the third one is a very rare phase, which is a third order topological insulator. So the bulk, surface, and the hinge, they all insulating, but there are gapless, zero modes on the colors. Okay. So of course, in this kind of use of method, there are also the bulk boundary correspondence. But however, we have to think about this more carefully because now we not only have the surface and the bulk, we also have hinges. So in this regards, we can think the bulk consists of the three-dimensional interior, and the boundary consists of the two-dimensional surfaces and the one-dimensional hinge. Or we can try to think the bulk consists of the three-dimensional interior and two-dimensional surfaces. However, the boundary is the one-dimensional hinges. So either one is fine, but we have to consider all three of them, the bulk, the surface, hinge, such that this bulk boundary correspondence will work. So with that, here's the outline of my talk. I'm going to give you three examples. The first example is the first ever topological insulator in the high order sense, which is a three-dimensional chiral one, which is actually the magnet-doped topological insulator. The second one is a topological superconductor, which can also be high order. The third one is a material that Min has introduced, which is bismuth cellerite and bismuth, the bismuth bromide and bismuth iodide. So in this type of materials, we can have hinge modes and the surface states, depends on the temperature, depends on the strain, and depends on the structure. So let's come back to the original Z2 topological insulator, the Kim-Melley type. There are two important symmetry of this state matter, time-reversal symmetry and the U1 gauge symmetry. So if we break the symmetries, we can get exotic states of matter. For example, if we have a domain wall on top of surface, there will be we can create a chiral-Majorana edge modes between the ferromagnetic insulator and the S-wave superconductor, or we can try to flip the magnetization of the ferromagnetic insulator. Then we can have this chiral edge mode along here. This is equivalent to a 2:1 integer quantum Hall effect. But however, this one is really challenging to realize. The reason is that it's kind of easy to have this surface state being captured by ferromagnetic insulator. But however, it's very hard to image where is the domain wall inside the ferromagnetic insulator. As such, it's very challenging to figure out where we should put the two contacts. And therefore, there's no way to detect the chiral edge mode, even though they exist. So to solve that problem, so what we try to do is instead of flipping the magnetization axis, we rotate the spin axis of the surface state by using two distinct surfaces. So this is based on the result that, if we gradually change the surface from top surface to the side to the bottom, the Hall conductivity, the quantized Hall conductivity, switch sign at the side surface. So therefore, if we have an ideal case, for example, we have a sphere, and as shown in this one, if the magnetization is in the Z direction, so everywhere it's gapped except the equator. Or in this more general case, suppose we have two surfaces, the projection of their surface normals, a switch sign across this hinge, there will be a chiral hinge mode. So everywhere is gapped except the hinges. So of course, we can also think about this very thin field limit. In this thin field limit, we only have top surface, bottom surface, and the side surface becomes very thin, and actually it's just a few atomic layer. And this is actually how people realized the Quantum Anomalous Hall effect in 2013. Okay, so I just show you a example of a second order topological insulator. So even ourselves, we didn't pay attention to that result back, like years ago. And a couple of years ago, people try to generalize our results, and really this field takes off. And at that time, people talk about different kinds of topological insulator of high order sense. And then we move one step further. We try to look for whether there is a possibility to have a high order topological superconductor. So the answer, of course, is yes. So the type of topological superconductor I work with is the one with time-reversal symmetry. So here's a cartoon that shows how to understand this special type of topological superconductor. So this is a kind of one-dimensional system, and there is a metal, and this is the Fermi energy. So we can try to think about the band inversion in this system. So first of all, the odd parameter acts as a master that gaps the Fermi surface. So a second, so in kind of system, there is a blue band, this inner band, and the red band, the outer band. So if the odd parameter switch sign from the inner band to outer band, then this kind of realize a topological superconductor with time-reversal symmetry. So of course, if we want to realize kind of state matter in high order sense, what we want to do is we try to realize the inner part at one edge and realize the red part of bands at the other edge. So this has something to do, has deep connection to do with the iron-based superconductor. Some of you are expert here. Okay, so that can be realized, if we couple a two-dimensional topological insulator and a extended S-wave superconductor. So if we have this kind of geometry, per color, there will be two Majorana modes, which form a Quantum pair. And if we solve this zero-dimensional pattern, what we will see is exactly the following. Is this one. So there is a superconducting gap. So within the gap, there are A modes, zero modes, two per color. Okay, so I'm going to use this cartoon to show you why this happens. So this is the blue band zone of the superconductor, and also the blue band zone of the topological insulator. Let's assume the lattice is a perfect match. Sorry, so there is a delay of this kind of. Okay, doesn't appear here. Okay, so this is the blue band zone. So the all the parameters switch sign from the zone center to the zone color. I'm not going to use this one. I'm going to switch back to this. Okay. It's kind of delay. Sorry about that. Okay. So there is all the parameters switch sign from the zone center to the zone corner. That's where I use the plus and minus sign to show them. And if we have a topological insulator sharing the same blue band zone, and the band inversion, the single band inversion occurs at pi zero, So if we project that a point to the horizontal edge, so there will be a helical edge mode right here. So that edge state feels kind of the superconducting potential all the way like this. So if we project this band inversion to the vertical edge, so the edge state will be here. And that actually feels a superconducting potential all the way positive. So therefore, it realizes a kind of a domain wall, right? And at a color, that's a color, there will be a Majorana Cramer's pair. So of course, this is it's a toy model. And then there are two kinds of materials that can realize this. One is the 112 family. So there is so this is a single UD cell. In this single UD cell, there is a very particular layer, is this AS1 layer. So that layer is a doped to the topological insulator, has a band inversion at pi 0, which is exactly the same as the model. And the rest of the UD cell forms a extended SOA superconductor, and therefore, per UD cell, you realize the toy model I just presented. And of course, it's very hard to get one UD cell out of the bulk material. Therefore, if we have a three-dimensional crystal, this color mode becomes dispersive along the Z direction. So therefore, they see there will be a Majorana hinge mode along the Z direction. So this is one interesting family of interesting materials. And there's another one that's FTS system. So there's an experiment that's done by a Cambridge group at Boston. So in this three-dimensional system, so we can try to think in this way. So of course, it's a superconductor. It has extended SOA pairing, and it's also the pairing material is also a doped 3D topological insulator. So therefore, there are surface state everywhere. And if this bulk surface proximity effect occurs and makes the top surface has positive SOA pairing, make the side surfaces have a negative SOA pairing, there will be a domain wall formed here, and there will be a helical Majorana mode right here. Let's briefly look at this experiment. So the bulk crystal, and people try to fabricate two kinds of contacts. So the first one, so contact contacts the top side and hinge modes. And the second type only contacts the top surface because there is a insulating layer here. Okay, so in this kind of a probe that contacts hinge mode below the temperature, below the critical temperature, one can see this a very sharp zero bias tunneling conductance peak within this U shape of superconductivity regime. And of course, we can also change the temperature. So they realized this peak actually disappear below the critical temperature of the FTS system. So of course, there are many experiments, there are many things we demonstrate in this system, but at least this gives us some initial hints. This system might be relevant for a second order topological superconductor. Okay, so now let's move to a third part, which is kind of the materials I've been working on for a number of years, and I already gave a wonderful introduction to that. So this is bismuth bromide and bismuth iodide system. So that system is pretty interesting. It can be viewed as a periodic stack of one-dimensional chains along the B direction, which is perpendicular to the screen. So as a matter of fact, there are two cleavage surfaces, which is the top surface, the O1 surface, and the side surface, which is a 1O surface. So this is the reason why we get into this material, because it has two cleavage surfaces. For weak TI, so the top surface, it doesn't have surface state. For side surface, it has surface state. We do need the multiple surfaces to demonstrate that. That's why we look for the quasi-1D one materials for weak topological insulator. And this material has many structures. The most interesting one are alpha phase and the beta phase. So this cartoon shows the difference between them. So in beta phase, so basically one layer per UD cell. In the alpha phase, there's a structure transition that becomes 2 layers per UD cell. And what's even more interesting is that one of them realized a high order TI. The other one can realize the weak topological insulator, as Min just mentioned. and this transition occurs at room temperature. That means there can be a switch on and off between the surface and hinge states near room temperature. Okay, let's try to understand, why that happened in this family of materials. So step one, we use two steps to understand that. Step one, so each monolayer is a 2D quantum Hall insulator with a very large gap. So this is our calculation for one of the four materials, the alpha phase bismuth bromide. We use a single layer. You see the helical edge mode appears, and the gap here is about 250 millivolt, which is 10 times of our room temperature. And if we calculate the state, of course, inside the gap, the density state is a constant because the density state in one dimension is just 1 over velocity. And here's the most recent experimental data from Zhihar Hassan's group, not APES. It's about STM. Okay, so what they try to look at is the time density state. The time density state at the surface or at the one layer step edge. So, okay, these blocks here. Let me use this one. So the blue curve, the light blue curve shows that there is zero density state within this energy range. So that's the kind of surface state gap. And if you move your tip to the step edge, you do see a finite conductance, almost a constant density state. That's kind of consistent with the prediction, but still there are variations. So what's more interesting is the fact that right at the Fermi energy, there is kind of this V shape in the deep in the tunneling density state, and it doesn't go to zero in that picture. Okay, let's imagine that doesn't go to zero. So that's actually due to the electron-electron interaction in this system. It's kind of a standard large liquid behavior. Okay, and of course, if we add magnetic field now, then at the Fermi energy, the density state, there's a gap opening, so the density state becomes zero. That's why this deep drops to exactly zero here. And if we increase magnetic field, so a gap at Fermi energy can become larger. That's why we see this flat red curve here. So of course, let's try to build a three-dimensional system based on what we just said. That's our step two. So in the beta phase, it's one layer per unit cell, and use the black line to denote a quantum Hall insulator. And this green dot is a kind of helical edge mode at one edge. And in this material, it's not phase. So why beta phase is so special? Because it has inversion symmetry and the two kinds of inversion centers. So one center is in between the barrier, is between the two monolayers. The other type of inversion center, you can place that on the top layer or on one layer. Okay, so because of that, the interlayer coupling are kind of the same. So this is kind of realize what we call the critical point of Su-Schrieffer-Heeger model, if you like. And that means the 1O surface and the minus 1O surface, they have two kinds of Dirac cones. Because you can imagine, so the time-reversal symmetry is protected at a kz equal to 0 and the kz equal to pi. So each of them has a Dirac cone. That's why we have two Dirac cones. This is standard, a weak TI picture. That's the critical point of the Su-Schrieffer-Heeger model. And in the alpha phase of butyl iodide, so the inversion symmetry is reduced in such a way that the inversion center can only be placed between two layers. So as such, there is kind of dimerization between the coupling of the edge modes in the side surface. So what's interesting is because this special inversion symmetry, the coupling at this surface and at the other surface, they are completely the same. So that means no matter how you truncate the system, the 1O surface is always gapped because of dimerization. But however, at a boundary, there can be some helical hinge mode. So this is some calculation that shows. Okay, 1 second. The top panel shows the the cartoon picture, the green ones are the hinge modes. So no matter how you terminate your system, you always have a pair of helical hinge modes, at top surface or at the bottom surface. That depends on the termination. And what's interesting is for the alpha phase, the inversion symmetry is also reduced, but the center can only be placed at each layer. So that will make the physics, kind of different than this alpha phase. So the dimerization on the left side surface and the dimerization on the right side surface, it becomes opposite. So that means if you terminate your system, you always have one helical hinge mode at the top surface and the one at the bottom surface, no matter how you terminate your system. So the calculation will show here. Okay, so that's what you see here. No matter how you terminate your system, you always get one helical mode on top surface, one at the bottom surface. Okay, so here is really the end of my talk. And I just want to mention, so at this point, there are a lot of experiments and theories going on about this system. And what's healthy is we do look at each other. So right now, theory is here, experiments are here. There is a gap, but I'm very confident, after a couple of years, so there will be a topological transition, and this will be reversed. Experimental people will stay here and look at our theorists. And if that happens, that's only because we have wonderful experimental collaborators and postdocs and students and all colleagues in the field try to make this be realized. With that, I thank you all your attention.
Okay, so are there questions? Yes, I'll bring the microphone so that we don't have to repeat as we did this morning.
Great, so nice talk. So with respect, sorry, my notes.
I'll take care.
So with respect to these are kind of questions more about the experiment, I think, than the theory. But so with respect to the edge modes in the topological superconductor, so are these chiral or helical?
Okay, so the question is in the topological superconductor, whether the hinge modes are chiral or helical. The answer is helical.
They're helical.
Because time symmetry is unbroken.
It's preserved. Okay.
Yeah. So it's D3.
Right, right. And so also in the case of the topological insulator, so you were claiming, well, I guess Hassan is claiming that the zero bias anomaly he's seeing is evidence of Luttinger liquid physics, but have they been able to do transport or any other measurement on these helical edges?
Okay, so I think people are doing transport right now, but the Hassan's experiment is kind of step edge, which is relatively easier. You have a bulk crystal, right? You just try to look for the step edge. You can use the AFM to identify whether it's a 1 layer step edge or 2 layer step edge. You just go to 1 layer step edge and try to look at the tunneling data.
So let me ask maybe a more broad question. So one of the issues with 2D topological insulators is that they're supposed to have these protected helical edge states. Mm-hmm. But in fact, they only ever seem to be protected over about a micron. And if you measure on scales other than that, you see what looks like diffusive transport. This is a big question,
Well, to some people, this is a big question, but to some people, this is absolutely not, because for example, it is not as the helical edge state is not as robust as the chiral edge modes. For example, you can add disorder. As right, certain type of disorder also is also susceptible to the pair what was that called? A kind of pair Zeeman fields. So if you have a square of the Zeeman field, that doesn't break time-reversal symmetry, but that can gap the edge modes.
Sure, but I mean, I guess my point is that it's not clear what's, at least from my knowledge, it's not clear what's going on in, say, mercury telluride. So is there some reason to believe that the helical modes in these higher order topological phases will be more robust or less susceptible to disorder or more controllable in some sense?
I think in the chiral sense is more robust.
More robust.
In the chiral sense is robust, yeah. So if you want to look at the details of how this conduction are different from 2e square over h, yeah, or why the perfect edge conduction only survive at, let's say, sub-micron scale. So I suggest you read the papers by Glassman at Yale.
Yeah.
He has a number of papers on that.
Yeah, I'm familiar with those papers, but those papers to higher temperature dependence than what is actually seen. But anyway, we can talk about
But the general sense is that, is kind of unstable to some interactions and to some disorders. Yeah.
Okay, anyone else? Yeah.
I've got a question to the first part of your talk. So we talked about the S plus minus superconductor.
Yes.
Notice that at no point did you show the Fermi surfaces. And the tacit assumption is that, well, all that matters is a gap changes sign somewhere in the Brion zone. So I'd like to point out that that's sort of a strong coupling assumption, very different from what we usually look at weak coupling PCS, right? So if I were to coming from weak coupling assumption, you would say, well, the gap is only defined within, a tiny region near the Fermi surface. So do you see that as a perhaps a hurdle, or under what conditions the statement that you could have the corner modes, let's say in 2D superconductor, and those Majorana corner modes, how sensitive is that to your assumptions about the global nature of superconducting pairing?
Well, that's a good question. Certainly, we never thought that deep, but so we let's see, the superconductivity is really a kind of background that provides a potential to the metallic states. So what I try to say is the superconductivity in the metallic states, this part is more normal compared to the superconductivity in the original materials. So once the superconductivity transfer out, it's more normal.
Right, but you see conceptually the issue that I'm pointing out.
Yeah, I see the issue. Yes.
Right? Like for instance, in the case of sort of Kane-Meili standard setup, if you imagine just putting aluminum strips, right, of a superconductor proximity induced on top of a 3D TI, you never worry about that, right? Because you're thinking of, first of all, K is not well defined here. You're talking about in real space, putting proximity superconductor. But if you are talking about a bulk material and the gap changing sign, I worry to what extent that, the fact that you're assuming it's across the entire Brion zone and that the gap is even well defined far away from
the question is, I think then for that question, then we just need, the metallic state to be fully gapped, So this guaranteed in that kind of scheme because, it's a topological insulator and the bulk is already, insulating, right? And the edge is conducting, but however, the superconductivity can gap it. So you can imagine the extended S-wave, so the zone center and the zone, they both, couple to the edge modes. But however, one of them must couple stronger to it. So therefore, you can always ask a question, what's the sign of the edge mode superconductivity?
Is it a really short question? Because we're kind of out of time. Okay, cool. So you again.
Okay.
And Daniel, maybe you can come and set up.